Okay, so today I'll be talking about the projectile motion first. So let's just handle this. So this is just the one type of two-dimensional motion, but it's a constant acceleration motion. So in this case, all right, this is the y-axis. All right, in this case, something is thrown to the air, right? So the object that you throw is called the projectile, right? And we are interested in the motion of that object, and we are going to analyze it, obviously. So what's important in here is that the acceleration is equal to the gravity, which is a vector pointing in the downward direction, okay? So for that reason, when people analyze these kind of problems, they choose axes in such a way that one axis is horizontal. Well, one axis is vertical. Usually this is the y-axis. So as a result, I'll just use this choice. And one axis is horizontal. Again, just keep in mind that, I mean, the choice of the reference frame is basically left to you. So as a result, you're completely free. You can choose the x-axis to be pointing upward to, or that axis might be pointing downward as well. So there are many choices. So the equations that you're going to write down is going to be dependent on these choices. So these are constant acceleration motion formulas. So the position is equal to the initial position plus the initial velocity times t plus 1/2 of acceleration, and the acceleration is in here is basically equal to the gravity, and the velocity is v0 plus g times t, right? These are the equations. There are these other equations as well, but these are the fundamental ones that gives the position and velocity as a function of time in terms of initial position and initial velocity. All right, just keep in mind that I sometimes write the letter V like that, sometimes like this. And for the letter G also, I have some alternative way of writing it down. So this is something that I cannot correct for some reason. So as a result, just keep this in mind. So this is the same symbol as this one. Okay. In any case, what we have said is that we can actually, let's see, we can, instead of writing these formulas, this is t squared, thank you. Instead of writing these formulas, I'm going to assign the homework later, right? So, all right, so I'm going to send the, I'm going to assign the homework later, but I said that it's going to take some time, 1 or 2 days, right? So we said that don't use the unit vector notation and things like that, just work with the components. As a result, the same equations can be written in the x direction and the y direction, right? I can write down the x component of the equations and the y component. What's important in here is that, I mean, for each of these vectors, I'm going to take its their x components and their y components and write them down in here. So I'll just do this for the vector g in here. So since it is vertically downward and the x-axis is horizontal, the x component is 0. And since the y-axis is pointing upward, but g is pointing downward, the y component of the gravity is equal to minus g, right? So as a result, in both cases, in here, I'm going to write down this, the first equation, for example. I'm going to write this first equation, but I'm just going to add these components. So for the x component, the equation is this. That's x0 plus v0x times t. And since the x component of gravity is 0, we don't have anything in here. Along the y direction, we have y is equal to y0 plus v0y times t plus 1/2 of the component of the acceleration is minus g. Okay, And now the second equation, so I'm just going to write this thing down. So x component of the velocity is equal to v0x, and we don't have the second term in here. And for the y component of the velocity is v0y plus the component of the acceleration along the y direction times t. Okay, so as a result, we will be working with these equations, but sometimes it will appear that, for example, you express one condition in the x component and the other condition, you look for a quantity in the y component, right? I don't know. I mean, we are going to ask for the horizontal range, for example. In this case, the question is, when the object lands, what is its position? So that basically corresponds to, in terms of the equations, when y becomes 0, what is the value of the x coordinate, for example, right? So as a result, I mean, from this respect, these projectile motions are a little bit complicated than the one-dimensional constant acceleration motion, but I mean, there's nothing complicated actually, apart from these kind of things. All right, and then I'm just going to write down these. The average velocity is equal to the arithmetic average of the initial and the final velocities. And I'm just going to write down this equation as well. So along the y component, along the y direction, I can write down all of these 4 equations. Along the x direction, I don't need to write down these equations because these are basically quite trivial because there is no acceleration along the x direction. And so therefore, along the x direction is just a constant velocity motion. Velocity doesn't change. So as a result, this is a very simple motion. Okay. All right. What else? Okay, so I'm just going to solve some problems in here. I just wrote the problems that my classical problems beforehand, so that I don't spend time writing them down. All right, this is just a usual projectile. It was thrown from here, from the ground level, with a speed of 100 meters per second and with this angle. And so the questions asked are the maximum height. I mean, these are some of the typical questions. Horizontal range. And in part C, I'm going to ask for the velocities of the object when it is at 140 meters above the ground, right? So it appears that there are these 2 points where the projectile is at that height, when it is still ascending, and when it is descending. So as a result, we have these 2 velocities in here. We are also going to compute those as well. Okay, I think I'm going to just pass down. Thank you very much for the quick answers. All right, all right, first of all, let's talk about this initial velocity, right? This is V0, initial velocity. It's just trigonometry, basically. I would like to find the x component and the y component of the initial velocities. So, yeah, as I said, this is just trigonometry. We are essentially computing these 2 components. So x-axis is horizontal, y-axis is vertical. And so as a result, this component can be written as V0 times cosine theta, and the other component can be written as V0 times sine theta. Okay, so in this case, V0 sine theta. Okay. In this case, there's also a convention that I follow. Right, so in homeworks, you are going to see these special angles frequently. So there's this famous 3, 4, 5 Pythagorean triangle. So in this triangle, sorry about that. Let me just make this a little bit bigger in here, right? So this is the famous 3, 4, 5 triangle. Okay, so this angle is very close to approximately equal to 53 degrees, and that angle is approximately equal to 37 degrees, right? So whenever you see these special angles in the questions, just understand that I'm basically writing down this special angle in here. So as a result, the trigonometric ratios are exact, right? So that means, I mean, cosine of 53 degrees is basically equal to 3/5 exactly. Right? That's what I imply when I specify this. For the y component, I said average velocity is v0y plus v. All right, I made a mistake probably in here. No, that's vy, right? That's the final y velocity. Initial velocity, final velocity, their arithmetic average is the average velocity over that time intervals. All right, that was the third constant acceleration formula. And that's the fourth. Okay. So in any case, so the initial velocity is therefore, I don't have space left in here. So cosine theta is 3/5. So therefore, this is 60. Yeah, I'm going to write it below, right? So as a result, this is 4/5. So that means V0x is equal to 60 meters per second, and V0y is equal to 80 meters per second. So along the x direction, therefore, it will be moving with constant velocity of 60 meters per second. But along the y direction, it does this usual motion. So the whole motion is a free fall motion. Again, just keep in mind, even when it is ascending in here, when it is going up, it is still in free fall. RBLOD, probably you won't need calculators for most of the things, but if you need, you can use, yeah, sure. Okay, so yeah, the maximum height, right? There's a next question somewhere in here, right? Okay, there's a condition for maximum height, right? So that's the point where the height is maximum. And we know that this corresponds to the situation where the y component of the velocity is equal to 0, because at that point, the velocity should become completely horizontal. Right? So therefore, the y component of the velocity is equal to 0. So that's our condition then. Vy is equal to 0. And I'm asking for the value of the y, the y coordinate. So what is the value of the y when it happens that when Vy becomes 0? Okay, so we can solve this problem in the usual way. So the x component of the motion has nothing to do with this particular question. So as a result, I'm just going to use this equation in here. V0y squared, final velocity squared minus initial velocity squared is equal to 2 times the acceleration times the displacement. Okay, I know everything in here except the displacement. Let's see. So that's the displacement then, delta y. Sorry about that. So that's that displacement. So that's equal to the height from the ground level then. So that's displacement. So that's the quantity that I want. In any case, this is 80. Sorry, final velocity is 0, and the initial velocity is 80, and the gravity is 10 as I have mentioned before, and the maximum height is in here. So we get like 6,400 in here, minus 20 in here. So from here, we find the height to be equal to 320 meters. All right. So I have the next question in here. So as a result, I'm just going to slide this sideways, right? So part B is the range. Right. So I mentioned this thing before. Basically, it leaves from here and then it reaches to that point. It lands in here. So the condition in here is that the y component of the position is equal to y0, basically, right? So this is the initial thing. All right. I didn't choose the origin in here, but it doesn't matter what the origin is. So the condition here is basically the displacement, y component of the displacement is equal to 0. And what we are asking, well, we are asking for the displacement along the x direction. Okay, so as a result, in that case, I need to write down both of these equations. Okay, so let me first of all write down the equation for the displacement along the x direction. It's a constant velocity motion, so therefore the displacement is this. Velocity multiplied with the time. All right, so as a result, I know this, so I need to find the time. Okay. So I need to find the displacement, obviously, but to be able to find the displacement, I need the time. So as a result, I'm going to use this condition to solve for time. So for that reason, I need delta y equation. I'm sorry. Sorry again. So this is the velocity is v0. That's the y component of v0. All right. Minus g times t squared. Sometimes I write this equation with a delta y, in which case there is no constant, or I just write y is equal to y0 plus something. Either way, right here, since I didn't set y0 to be anything, I need to compute the displacement, right? In any case, so this is 0, so that's our condition. V0y, that's 80. Actually, it's plus 80, but in any case. And the gravity is 10. So I need to solve this equation. I think 160 in here. So the equation is 16t minus t squared. There are two solutions. All right, both solutions have a physical meaning. So the first solution is basically about here we are finding the time when the object is at the ground level, right? There are two times that this happens, right? At the time it is thrown. And so as a result, this is basically about the initial point. And at the time it is basically it lands. Right? So as a result, this is the solution that we want, obviously. Okay, I just wanted to repeat this. So as a result, then delta x can be written as, again, this should have been v0x. Yeah, sometimes I write vx0, sometimes v0x. That's one of the things that I get confused also too. All right, so that's 60 multiplied with 16, which is 30 to 960 meters. Okay. Okay, can you find the time by using this equation? Vy is equal to v0y plus minus g times t. Yes, you can. You know that the At this point, it is passing from the same level. So as a result, the velocity is the negative of the initial velocity. So that's minus 80. Initial velocity is plus 80. So that's minus 10. So therefore, this t is equal to 16 seconds. Yes. 8 seconds isn't. So there's a final y velocity in here. Okay. Velocity of y becomes 0 at the maximum point. When the object is passing through the same point, the velocity of y becomes the negative of the initial velocity, right? If you remember, yesterday we have discussed this. So when the object is passing from the same point, same level here, same y coordinate, it has the velocity changes its direction. It has the same magnitude, but it changes its direction, right? So initial velocity is plus 80. So the final velocity will be minus 80. Right, I'm just going to draw some of these in a moment. So as a result, this is the correct way of doing this. Okay, I'm going to pass to the side again. So part C. So the question is, what is the velocity? All right, so we have a certain height in here. 140 meters. Just remember that the maximum height is 360 meters. So in any case, I mean, there are actually these 2 points where the object reaches to that height, right? Let's just draw these. At one point, it will be ascending. At the other point, it will be descending, right? So that's the ascending one. Why don't we write down the velocities as VA and this is VD? Okay, and we would like to find these. Okay, I can solve the problem like that, right? You can find the time that the projectile reaches to that height, right? So as a result, you need to solve this. H is equal to, yeah, whatever. V0y times t plus 1/2 of minus g times t squared. All right, you can do it like that. So you get a second order, you have a quadratic equation with 2 solutions. So you get two solutions in here. That's a possibility. You can solve it like that. Or we can find, and then use the other equation for the velocity and just find the y component of the velocity. Or we can find Vy directly. Okay, that's the equation that we need to use because I don't need the time. I don't need to compute the time in here. Right, let me write 2ay delta y, right? I can use this equation because I know the displacement, I know the acceleration, initial velocity is known, so that's the only thing that I need to find. That's also a quadratic equation. So in any case, I can solve this. So in any case, the acceleration of y is minus g, and the displacement is obviously plus h. So acceleration and the displacement are in opposite directions. So the right-hand side is negative. When it is above, I also know that the speed is smaller than the initial speed. So therefore, the left-hand side is also negative, right? But in any case, let's just write this thing down. So that's 80 squared. And on the right-hand side, gravity is 10. And that distance is 140. So that means 280 something. I don't want to write down the units. So this is 6,400. So Vy squared is therefore, sorry, there's a negative sign in here. 6,400 minus 2,800, which is 3,600, all right. So therefore, there are these two solutions in here. It's either plus 60 or minus 60, and the unit is meters per second. Okay, there's a warning in here. We're not, the question is not asking for the speed, it's asking for the velocity, right? That's something that you have to be careful. All right, so in any case, so it appears that, therefore, I'm just going to draw it like that. I think I'll keep using this pink color perhaps. So it has an x component of velocity, which is 60 meters per second, and a y component of the velocity. In that case, the y component of the velocity is 60 meters per second. Okay, or it is minus 60. So obviously, the y component of the velocity is minus 60 when the object is descending. So it's at that point. So in all of these places, the x component will be 60 meters per second. Okay. So obviously, the x component of the velocity is the same all the time, right? That's equal to the initial velocity and velocity at all points in the motion. Okay, so but the y component of the velocity changes, so it's plus 60 in here, minus 60 in here. All right, another rule, when the object is passing from the same level, right? Let's talk about this particular level in here. So it is passing in here when it is going up, and it is passing in here when it is going down. So the y component of the velocity in both cases should have the same magnitude and opposite direction, and we see that this is the case in here. All right, so let's also state this. In any case, let me just write down the answer in here. In terms of the x and the y axes that we have provided at the beginning of the problem. So that's basically 60I plus 60J meters per second, let's say, when ascending, and the velocity when descending is 60I minus 60J meters per second when descending. Okay, so this is the answer for the velocity, right? It's not the speed in here. All right, because velocity basically is a quantity which has a magnitude as well as a direction. So you have to provide both of these information. Right? And one way of doing this is to do the unit vector notation. So therefore, this is the correct way of answering, right? There's another way of providing the same answer in here, for example. So you can provide the speed, which is 60 root 2. Let's just write down the exact answer in here, meters per second. But this is just the speed only. It's not the velocity. That's not the same thing as velocity. Okay. So if it is the speed only, sorry, if you want to give the magnitude somehow, you force yourself, you think that you have to give the magnitude, and you don't like to use the unit vector notation, for example. In that case, to specify it as a vector quantity, you also have to specify the angle as well. So let's say it like this: at an angle of 45 degrees above the horizontal. Okay, so if you give this full answer, then that means you have specified that vector quantity because you have given both the magnitude and the direction. So as a result, that answer is mathematically equivalent to that answer, right? You have provided the value of the vector quantity. Otherwise, if you just give this value, you're not specifying the vector in here, okay? So that's important actually. So when we are saying a vector quantity, it's different than sorry, let me first write this thing down. It is different than the scalar quantity. It's different than the magnitude, right? There is always a direction information that you have to provide. So, I mean, I said that, well, it's basically a different kind of a quantity because you have to use this unit vector notation, for example, for specifying it. It's a different kind of a quantity. So as a result, you cannot describe a vector by using a single number only. VAY is not 80. Why do you think that it's 80? Initial value V0Y is 80. All right, so let me just add one more part in here. Sorry. So this was the thing. So let's say it like this. So I'm just going to add this. So find velocities at, let's say, different points on the trajectory, let's say. All right, I'm just going to do this for some kind of an extra information, but I'm just going to look at these 5 special points. Okay, so there's this initial special point. So I'm going to use the yellow color in here. So this is V0. All right. My drawing is horrible. All right, I'm just going to draw it like that. All right, this is V0, the initial velocity. V0. That's equal to 60I plus 80J meters per second. Okay. So I know, yeah, let me write this thing down. So that's at a height of 140 meters above the ground level. So this is, at this point, the velocity is VA. So that's 60I plus 60J meters per second. So the X component of the velocity remained the same. The Y component of the velocity somehow decreased somehow, right? So at the topmost point, so let's call this as V top. So in that case, this is 60I meters per second. So at the topmost point, the Y component of the velocity became 0. And when it is descending, right at that point, so this is VD, the velocity is 60I minus 60J meters per second. So that means the Y component became negative. The Y component changes continuously. So as a result, at this point, the Y component, let's say V landing here, landing velocity. So that's going to be 60I minus 80J meters per second, right? I think I'm going to squeeze it somehow in here like that. All right, let me use a pink color in here. So in all of these cases, the X components of the velocity, all X components are the same. but the y components changes. So first it starts from a positive value, decreases, becomes 0, becomes negative, becomes more negative, right? So as a result, I can draw the components like that. So for the x component, it's always like that. So all the x components are the same. All the x components are the same. Yeah, whatever. I mean, they should be supposed to be the same. All the y components, however, they differ. So yeah, whatever. It becomes 0 in here, negative downward in here, and more downward in here. Okay, this is on the trajectory basically. In each case, the velocity is tangent to the trajectory. I can draw all of these vectors like that. Let me use a yellow color again. So this is the initial velocity, V0. This is the velocity, VA. This is the velocity at the top. Right? I basically draw all of these velocities starting from the same position. So I just shifted them and made sure that they start from the same position. So this is VD and this is VLand. Okay. In all of these cases, the tips of all of these vectors are on the same line. And the reason is that, well, basically the changes in the velocity is in here, like this delta V, for example, right? All the changes in the velocity should be parallel to the gravity. And this is downward. Right? Because of that reason, all of these vectors have the same horizontal component. Right, I mean, you can view it in this way too. Okay, so I think I'm done with this problem. Yeah, it just took me 1 hour to solve a problem. Do you have any questions about that?
Hocam?
Yes.
About when we expressing velocity, doesn't the signs express the vector when we put signs?
I mean, for this one, for example, saying that V dy is equal to -60. You're talking about the sign in here.
Yeah.
Yeah, it contains the direction information.
No, I mean, we said that there are two expressions when we say it's a velocity.
Yes.
I mean, yeah, there are two, and we can say that. Can't we say that? I mean, V dy is equal to -80,
yes,
-60 meters per second, and V dx is equal to
+6.
Yeah.
Yes.
We can say that then it's a velocity, right?
Yeah. You just give both components separately. Yes, you can do that.
Yeah, all right.
And yeah, by giving the components separately, you also give the same information.
All right.
True. VLand minus VD is not equal to VD top. No, it is not. So different time passes between these points. So the time between these 2 points is not the same as the time between these 2 points, right? Because of that. Okay, so I think I'm going to pass to this next problem. All right, this is a very simple problem. I think I'm going to solve some simple problems. Then in the second hour, I'll talk about this maximum range problem. So this is a military application in a way. So you have a rifle, you're firing it horizontally towards a target. All right, let's say that the target and the rifle they are in the same level. So you just aim it horizontally and then fire it, right? But because of the gravity, the bullet is deflected, and we would like to find how much does this get deflected, right? So these are some typical values. So this is like the muzzle speed of the bullets is typically around, for military rifles, This is around 1 kilometers per second. The ordinary rifles for hunting, for example, probably have a lower muzzle speed, basically. For the handguns, it's even lower, but I think it's like a few hundred meters per second or something like that. Okay. In any case, so let's say that when the target is about 100 meters away, how much does it get deflected, right? It's just a common order of magnitude question, essentially. So as a result, from here, we can then understand if we need a correction for the effect of gravity. Okay, so in any case, so that's a very simple thing in here. So in this problem, V0x is equal to V0 and V0y is equal to 0, right? So as a result, when the object hits the, when the bullet hits the target, let's say, in that case, the distance traveled in the horizontal direction is given by that expression, so it's V0t. But the displacement in the y direction, which is minus h, is given by, by this expression, but this term is equal to 0. So this basically says that we essentially have a free fall in here, free fall from rest along the y direction. So as a result, the distance it falls is given by this famous formula. So there is no initial velocity in here. So what we need to do, therefore, is to take the distance, take the time from here from that distance. So that's 1/2 of g. And we have distance divided by V0 squared. Okay. I think the important point in here is that if the distance is doubled, for example, the time to reach to the target is also doubled. And so because of that, the distance traveled in the horizontal direction is quadrupled. So h depends quadratically on the distance of the target. Okay. So in any case, for this thing, the time is equal to 0.1 second. And so therefore, h is equal to 0.1 squared. So therefore, this is like 0.05 meters. So it's 5 centimeters. So the deflection is quite small if you want to hit a target, which is quite large, perhaps. If you are firing at a person, then that's negligible. In any case, so because of that quadratic dependence, I would say that therefore, so that's part A. Let's say it like this. If the distance is not 100 meters, but 200 meters, in that case, the bullet misses by 20 centimeters. And part C, if the distance is 1 kilometers, in which case it is 10 times bigger. I mean, the distance is 10 times larger, in which case this is going to be 100 times larger. So that means this is going to be 5 meters then. Okay, so as a result, I mean, if the target is too far away, then the missing distance is actually quite large. And because of that reason, if the target is kind of far away, in that case, you have to somehow take care for these kind of effects should be taken into account, right? So they do this in a very special equipment. So there is some kind of a way of taking an aim. So when you do your military duty, you're going to learn about this. But in any case, it's one of the things that I need to mention, okay? I needed to mention, but it's not something that's too much important. All right, let's have a break. After the break, I'll be talking about this maximum range problems, and then I'll see what I will talk about.